Hey everybody, so we're going to talk about confidence intervals again today, and we're going to follow along with Scott Stevens' Introduction to Statistics, Think and Do, like we have been all semester. And today we're going to talk about confidence intervals again, and this time we're going to be using confidence intervals to estimate a population mean. And we've estimated population means before. If you'll probably recall that the general form of a confidence interval for population mean looks something like, we think mu is between x bar minus some margin of error and x bar plus some margin of error. And that's going to be the same general form for a confidence interval for a mean here. The only difference between this time and last time is now we're going to assume we do not know sigma. And this is a much more realistic scenario because if we knew sigma, if we knew the population standard deviation, then you would probably know all the population data. And if you didn't know that, then you would be able to calculate mu. You wouldn't need to estimate it. So this is the more realistic scenario that if you're trying to estimate a population mean that you don't know, you probably don't know sigma. And so let's go ahead and talk about how to calculate it. It's going to be, again, we said it's going to be a very similar form, basically the same general form, and now we're just going to have a different E formula here. Okay, and if you creep down the page a little bit, this is going to be the new E formula, and we'll talk about what the parts of this formula mean in a moment. So a little bit of background here. The Z distribution is a distribution that we've been using so far, and now we're going to introduce this thing called the T distribution. So suppose we take samples of size n from a population with mean mu and standard deviation sigma, then the values of this expression right here, these are basically just z-score values, this expression right here, follow a standard normal distribution we found. Okay, well what if we don't know sigma? Well, what's the next best thing that we can use if we don't know sigma, if we don't know the population standard deviation? Well, some of you might guess sample standard deviation, and that's absolutely right. That's what we're going to use. So instead of using sigma, let's use S, the sample standard deviation. And it's going to turn out that the values of this expression right here actually follow a pretty similar distribution to the normal distribution, but it's not quite normal. And it depends on the sample size. It's actually a bunch of distributions. It's a whole family of distributions. And we call this distribution the student T distribution. T, because T is the letter that we use to denote the variable. You'll see down here, we call it T sub alpha over 2. So our critical values are called T critical values. And student, interesting story behind that. Where this first came from was published in a paper, and it was published by a statistician who didn't want to use his real name. And so he published it by the pen name student. And that's why it's called the student T distribution. So what's the difference? Really the only difference here is that you're just using S instead of sigma. And they're basically the same thing, so there's really not a huge difference here. But I guess the difference for you guys is that instead of using the Z values that we've been using, we now have to use these things called T values from another table. So the author has some notation and formulas here. A lot of these are very familiar to you. Mu is the population mean, which obviously is unknown because that's what we're trying to estimate. X bar is the sample mean, we know that. S is the sample standard deviation. You guys should recall that from earlier this semester. N is the sample size. You guys better be familiar with that by now. And this right here is a new term right here, and it's called the degrees of freedom, and we denote that as df. The degrees of freedom is one less than the sample size. Degrees of freedom is actually a pretty complicated statistical situation. But for our purposes, really all we need to know for right now is that the degrees of freedom is going to be n minus 1. Okay, so just take your sample size, subtract 1, you got your degrees of freedom. And if you have that, as long as you're cool with that, then you shouldn't really have much problem finding these t sub alpha over 2 values. Okay? Confidence level, we know that. Alpha is the combined area in the two tails of the distribution, aka 1 minus your confidence level. And t sub alpha over 2 is this critical value that we're looking at, and e, of course, is the margin of error. So let's scroll down, and let's take a look actually at this t sub alpha over 2 table. So this is on page 290 in the back of the book. And we have this table here. So basically there are just two things you need to look up. One, there's a typo in the textbook. It's confidence intervals, of course. So you look at what your confidence interval is, what's your desired level of confidence, and then you go down to your degrees of freedom, which is subtracted 1 from your sample size, and that would give you your t sub alpha over 2. And then it's just basically the same procedure as we've been doing before. Okay, so back in section 7.4, your E is just going to be t sub alpha over 2. You look that up in the table, and you times that by S, your sample standard deviation, over square root n. Very similar to our old E formula, which was Z sub alpha over 2 times sigma over root n. Right? Incredibly similar. Okay, so to use the t-table, you get the appropriate row by finding your degrees of freedom, where degrees of freedom is n minus 1. Just talked about that. Then you get the appropriate column by finding your confidence level, which is pretty easy. And this table in the back, you'll notice, has all of the confidence intervals stated right above it. Some textbooks don't have that, so this makes it even super easy for us. And then you just look up your t sub alpha over 2 value just by matching up the row and column. Pretty easy. So some requirements that must be met in order to use this method. One is that the sample must be a simple random sample, and 2, the sample size must be greater than 30, so n has to be greater than or equal to 30, or the population has to be normally distributed. One of those two things. And that was the same case for our z sub alpha over 2 also. So those requirements stay the same. Okay, so the procedure for calculating confidence intervals is almost identical to what we did before. We know it's going to be that mu is going to be between x bar plus some error and x bar minus some error. And we just have to find our e value, where e is going to equal t sub alpha over 2 times s over root n. Okay? And, write an understandable concluding statement, such as I am, 95% confident that the mean for all such and such is between your lower bound and upper bound. There are a couple round-off rules listed here. When using raw data, round to one more decimal place than used for the data. I think that's a pretty good rule. And then it says when you only have x bar, use the same number of decimal places for x bar. That's a fine rule. You can use that if you'd like. If you want to go one more decimal place, I think that's perfectly fine as well. I encourage you to use your own judgment there. Okay, example 1. A simple random sample of 35 men yields a mean heart rate of 72 beats per minute and a standard deviation of 10.2. So first, this standard deviation, the wording of the problem, does it infer that or imply that this 10.2 is a population standard deviation or sample standard deviation? Think about that for a moment. Well, I think it would be a sample, because it says the simple random sample of 35 men yields this mean heart rate and this standard deviation. So these are both yielded from your sample. Okay, so it's not explicitly stated that it's a sample, but I think it's pretty clearly implied. So this right here is your S. So therefore, sigma is in fact unknown. So when sigma is unknown, we need to use our t critical value in our error formula. Okay? So that's going to be our general form up there. I'll write it again over here on the side. That me is between x bar minus your margin of error and x bar plus your margin of error. And now we just got to find this e value. So e is going to be t sub alpha over 2 times s over root n. Well, what is our t sub alpha over 2? So t sub alpha over 2, we need to know two things. We need to know our confidence level, and we need to know our degrees of freedom. So 95% confidence level, and we have a sample of 35 men. So since we have 35 men, our degrees of freedom equals 35 minus 1, which is 34. So now we're going to go to our table on page 290, and we'll go to 95% and degrees of freedom of 34, and yep, that's our 95% column. So here is our t sub alpha over 2 value, 2.032. 2.032. So that is where, in our example on page 114, we have a t sub alpha over 2 of 2.032. So our e is 2.032 times s over root n. Well, our s is 10.2 divided by square root of n, which is 35. You're still using your n here. You're not using your degrees of freedom. Okay, then you punch this baby into your calculators, and that'll give you your error, which turns out to be about 3.50. Okay, and then I'll let this example take it away. We're going to do x bar minus your error, x bar plus your error. So it's going to be 72.5 minus 3.5 and 72.5 plus 3.5. And that'll give you 69.0 and 76.0. So we get a confidence interval of 69.0 and 79.0. Okay, so we are 95% confident, because that's the confidence level we're working at. We're 95% confident that the true population mean pulse rate for all men is between 69 and, oops, that shouldn't be a 79, that should be a 76. And 76.0. Okay, cool. And also, the calculators can do this too. I mentioned this in class that you guys should look this up. So let's put some of this into our calculators. Let me show you guys real quick how to do this. So you may have to rewind and look over this too. So you're going to go to Stat, you're going to go to Tests, and there's a bunch of different tests or things in tests that we can use here. And we're going to go to t-interval. So t-interval right here. We're going to input statistics into our thing because we don't have raw data to put in. It will work with just the raw data, but we have statistics. Our x bar is 72.5. Our standard deviation, our s, is 10.2. Our n is 35. Our confidence level is 0.95. And it gives us, does some crunching, and it says 68.996 and 76.004, which when you round them, you'll get the same values that we got over here. Awesome. Pretty easy stuff. And also, in the tests, you'll also see some things here. You'll see z-interval, which is the methods that we did in section 8.2. They're really not quite applicable, not realistic scenario if sigma was known to you and you wanted to find a confidence interval. And also down here is one prop z-int. One prop z-int. And prop stands for proportion. So that's when you want to do a confidence interval for a proportion. Okay, and all right, so let's take a look at the your turn here for part B, and I'll encourage you guys to pause the video here and try this on your own. And then when you replay the video, I'll go through my solution and we'll see if yours matches up. Okay, let's give it a shot. So first thing we need to find is the critical value of t, our t sub alpha over 2. That's going to be critical, for our error formula. So to get the critical value of t, you just need two things. You need your confidence level, which in this case is 99%. And the other thing you need is your degrees of freedom of n-1. And there's no new information given here, so we're just going to go with our degrees of freedom from the information given to us previously, which is 35 men. So the degrees of freedom would be 34. Okay, so let's go to the table now. And we are looking at, 99% confidence level and 34 degrees of freedom. So we're going to go down from here all the way to 34. Boom. So this is our new t sub alpha over 2 for this example. So our t sub alpha over 2 is 2.728. 2.728. So our t sub alpha over 2 is 2.728. Okay, so that means our margin of error is going to be that 2.728 times s over root n, so 10.2 divided by square root 35, and you calculate this baby out, and what do you get? You get 2.728 times 10.2 over square root of 35 is 4.703. 4.703. So let's just go with 4.70. And then our confidence interval is going to be x bar minus this error and x bar plus this error. So we're going to get that the mean is between, we got to do that subtraction and addition. Let's see. What was our x bar? 72.5. 72.5 minus 4.7 and 72.5 plus 4.7. All right, so our boundaries are going to be 67.8 and 77.2. So 67.8 and 77.2. All right, and so we can say we're 99% confident that the true mean pulse rate of all men is between 67.8 and 77.2. All right, so that'll do it for section 7.4. I'll see you guys in class, and I'll see you then.